This next question talks about spacecraft that have been to planets such as Venus and Mars, and the spacecraft has sent back information about the planet, the atmosphere of each planet. So talking about the gases that are there within each planet. The main gas in the atmosphere of Mars is carbon dioxide, and they're asking us to explain why in terms of structure. So we need to talk about the structure. Carbon dioxide is a gas even at low temperatures. So it's got to be a reference to the fact that temperatures are low, and if remember, if temperatures are low, energies are also low. Okay, and we've got to talk about the fact that it's a gas in terms of its structure. Okay, so the first thing we need to say is what the structure of carbon dioxide actually is like. So carbon dioxide, remember, is CO2, and it's a simple molecule. Okay, so the first thing to mention is it is CO2, or carbon dioxide, is a simple molecule. So what does that mean about the forces and the bonds in terms of the structure within it? Okay, so remember the forces, the intermolecular forces or the intermolecular bonds are weak. The intermolecular forces or bonds are weak. Therefore, only a small amount of energy is needed to overcome them being the forces. So CO2 is a simple molecule, the intermolecular forces or the intermolecular bonds are weak, therefore only a small amount of energy is needed to overcome them. Okay, so that's why it's a gas. Only a small amount of energy breaks apart these intermolecular forces, therefore the particles are spread apart, and therefore we know it's going to end up being a gas because the particles end up being further apart. I've got another question here, again based around structure and bonding, this time looking specifically at silicon dioxide. So it's used for lining furnaces. So we know furnaces are very hot. Okay, so this question is going to have something to do with temperature within it. Okay, they're saying that these furnaces can be used to melt iron for recycling, so it must be very, very hot. The diagram shows a small part of the structure of silicon dioxide. Okay, so you've got oxygen atoms and silicon atoms here. Each oxygen atom has 2 silicon atoms attached to it. Each silicon atom has 1, 2, 3, 4 oxygen atoms attached to it. So we can see the structure. There's one silicon, there are the 4 oxygens around it. Okay, there's one oxygen, it's got 2 silicons attached to it. Another oxygen, 2 silicons attached. Okay, so explain why silicon dioxide is a suitable material for lining furnaces. So because of this structure, silicon dioxide has a high melting point. So this means that there's a lot of energy required to break these bonds. It has very strong bonds, and it's in a giant structure, as we can see here. It keeps repeating the same structure, one on top of the other. So it has a giant covalent structure, which means a lot of energy is needed to break the bonds. Okay, so where I'll get my marks from this, first one is saying silicon dioxide has a high melting point. It's a giant covalent structure, so saying it's covalent gets you 1 mark, saying it's a giant structure gets you 2nd, which means a lot of energy is required to break the bonds, gets you the 4th mark for that one. Right, I want to move quite swiftly onto something else right now, sort of related to bonding, more looking at the formulas, which is another area that comes up quite often. So looking at how we can actually calculate something called the empirical formula. So what the empirical formula actually is the actual, well, the simplest formula for a compound, and we have to do calculations to find them out quite often. So here's a typical question for that. So you've got a sample of copper nitride, which contains copper nitride, which contains 3.81 grams of copper and 0.28 grams of nitrogen. Okay, so you know exactly how much mass of each you have. They're asking you to calculate the empirical formula, and they're saying show all your working. Okay, that's the only way you can get full marks for this question. They've given us the relative atomic masses. Okay. They've given us the relative atomic masses, in other words, the number of neutrons and protons in the actual atom. So they're giving you the one for copper, which is, remember, it has a decimal place within it, and the one for nitrogen as well. Okay, so let's have a go at calculating this. What you actually need to do is to take the mass and divide it by the relative atomic mass for each of them. Okay, so you need to do that for copper, and you need to do it for nitrogen. Mass divided by relative atomic mass. So let's do that. So we've got 3.81 divided by 63.5, and then you've got 0.28 divided by 14. Okay, so you can see that up here. Copper with copper, nitrogen with nitrogen. Okay, right. So the numbers we get for that are 0.06 and 0.02. So now we've got to look at those numbers, and we need to get them into whole numbers, where you know for every however many of copper you have a certain number of nitrogen. So the easiest thing is get these to full numbers first. Instead of having those decimal, let's round them up to the nearest full number, to the easiest full number. So I could make that into 6 by timesing by 100. So if I times that by 100, I've got to times this one by 100. So it ends up being 2. So I times both of those by 100. So that gives me a ratio of copper to nitrogen of 6 to 2. Well, can I simplify that? Yep, 3 to 1. That means for my 3 coppers I have 1 nitrogen, and therefore I have my formula of copper nitride, Cu3n. Remember, the 3 needs to be subscript. One of the other things I like to add to this is doing work to do with something called gas chromatography, which is also spoken about quite often in bonding as well. And it's one of those questions that comes up every now and again that people quite often sort of forget how to answer. So I'm going to quickly go through the process of gas chromatography here as well. Okay, so in so this question over here has a bit about gas chromatography. It says compounds from food packaging must not contaminate the food. Food can be tested for contamination using gas chromatography linked to mass spectroscopy. So that's what the GCMS stands for, gas chromatography, mass spectroscopy. Gas chromatography can separate substances in a mixture of compounds. Describe how as fully as you can. So let's describe. We're not explaining how it works, we've just got to describe how it actually works, what actually happens. Well, the first thing is that substances, whatever substance we're looking at, is carried by the gas. So substances are carried by a gas. Okay, and they're carried through a column. Sometimes it's called a coil or a tube, and sometimes it's mixed with a solid or a powder. Okay, so carried by gas through a column is the easiest way to put it. Okay, so the mark so far, substance carried by gas through a column. Okay, now because the substances have different properties, they go through the column at different speeds. So they travel at different speeds. So remember, I don't need to say, oh, it's to do with their properties, that's why they go at different speeds, because it's only a described question, not an explained question. Okay? Another way of saying at different speeds is different retention times. So in other words, they're kept within the gas for a different amount of time. So sometimes you get this information called a molecular ion peak, okay, which I highlight for you. The molecular ion peak gives you certain information about the molecule. What it tells you is the relative molecular mass. Molecular mass. Not the atomic mass, but the relative molecular mass. Okay? So that's in other words M subscript R. It's also known, okay, as the formula mass. Okay, so you could have done that. Yes, it eventually tells you the substance of the molecule,